Thank you for the great introduction. Well, I think I can go very shortly about it. Most has already been said. What's probably important to mention is that indeed I train a lot, even though I'm not only a trainer, I also try to work in projects. That's what I try to do most of the time. And actually help developers, no matter they're Kotlin or not, in all stages of their Kotlin development or on their Kotlin journey, being beginner, intermediate, or advanced. So actually also the more advanced courses are the ones that are quite trendy for people that program Kotlin already for even years. So there's still a lot to learn also when you are experienced. Certified. When you look at my career, I started out with Java about 20 years ago, moved over to Scala about 10 years ago, and since about 5-6 years I mostly write backend logic in Kotlin. The talk I'm going to give today definitely has some roots in my time with Scala, where, well, we still had to find the balance. So the result of this journey, including what I did with Kotlin, is kind of accumulated in this talk. Okay, that enough about me. I'm actually quite curious to know a little bit more about you. You already know quite a lot because we had a lot of hands ups and down, but in this regard I would like to know a bit more about your background in functional programming. So who of you does functional programming on a daily basis? Okay, that's quite decent. That's quite good. Who of you has ever written a higher order function? That's good, nice. So who has heard the term monad? Okay. Who knows exactly what it is? That's less. Okay, cool. That's what I would expect. So, well, me included, I don't know. I think you're never going to know it. Okay, so then let's hit the road and start our hopefully transforming journey, which starts in a place where you probably don't like to be, which are the swamps of imperative programming. So, why is swamps associated with imperative programming? I think we first have to elaborate on that. Well, when you differentiate the programming styles we have out there, then I think we could come up with two large groups. So the first group would be imperative programming. And imperative programming relies on this concept of declaring variables which are then mutated along the way. That's what imperative programming is about. And the code sample you see here basically depicts this particular paradigm. The language feature we use when you use Kotlin are mostly vars, loops, the mutable aspects of Kotlin, like the objects collections, and here and there a bit of return, right? So you process your stuff when you think, oh, now it looks good, return. Okay, let's go on in this condition, oh, I think now return. The counterpart of imperative programming would be expression-oriented programming. That's not yet functional programming, but it's definitely at the foundation of functional programming. So what does this entail, expression-oriented programming? It basically means that you start thinking in functions that take some input, transform it to some output, which again can serve as some input. And as such, it goes on. The example you see here is actually the exact same code on the left, but then rewritten in an expression-oriented style. So what kind of constructs are we using in this particular style? We use the immutable features like data classes, vals, immutable collections, expression constructs. So maybe you see the expression construct here, which is a try-catch. So in Kotlin, try-catch is expression, which means that it returns a value. Right? The statement produces some side effect, and expression returns a value. And try-catch is an expression because it returns. And of course, high-order functions. So what's really fundamental about these two ways of programming is the way we think about software. In imperative style, we think in terms of data mutation and side effects. That's kind of the hammer we use to build our logic. In expression-oriented counterpart, instead of mutating data, we think of data transformation and very strongly to this input-output thinking. So once I started to embrace expression-oriented programming, I really became a better programmer. And why is that? So why can we say that this way of programming leads to better software? Well, there are quite good reasons. Quite a few and good reasons. So first of all, that's what you see in the sample itself. It's considerably concise, right? Shorter, crisper, than what you see on the left. That's for one. It's much more expressive. Why? Because we actually program on a higher abstraction level. On the left, you have these loops, these if, these else, which are just kind of very low-level constructs. On the right, we express our intent with things like filter, max, by, or null. So we actually program on a higher abstraction level. And as such, we're more expressive. What's also interesting is that because we have this input-output thinking, we are much more deterministic, because every input leads to an output, which also enables us then to test this output. When we just produce a side effect, what are you going to test? Because you don't really know what changed. Maybe you know when you sort that probably a correction has been sorted, but maybe something else has changed too. You don't know, for sure. What's also very interesting is that when you look on the left, when you declare this variable on top and then you process them, the scope of a single variable is much larger than on the right. On the right, the scope we have to kind of manage in our mental space is actually only the function that is transforming some input to output, which is very small. Whereas on the left, such a variable can be very long. I've seen that in IntelliJ you even have tooling that kind of shows you which variable is used where with coloring to kind of still make a kind of sense out of it. But if you use this expression-oriented style, that's not even needed, right? Because the scoping is much smaller. So reasoning about code is simpler. And I think that's also not a kind of luxury to have. The code on the right is also safer. So for instance, I could very easily omit these lines here on the imperative part, and my code still compiles, right? Whereas on the left, I couldn't even make this mistake. So these are compelling reasons to try out expression-oriented programming. And should you not have done it yet, then I strongly advise you to try it out. So maybe just out of interest, so who of you is merely using this imperative programming style? Not anymore, okay, after this kind of, okay, a few ones, and the others are using, I guess, mostly expression-oriented programming. Cool. Okay. I think keep on doing that. For the ones that are still doing imperative programming, perfectly fine. I would invite you to try it out, and you won't be disappointed. I quite can reassure you that. Okay, so from these swamps, we now moved a bit further into this valley of expression-oriented programming, which is definitely a greener place to be, but, well, we're not yet at a place where we have a nice view, right? Maybe we can still go a bit further. Let's see. When it comes to function programming, mostly the focus on function, but, well, every function takes input and output, right? So the data types we transform, they're also very important in functional programming. And the good news is that the concept with these types are also easily connected to domain-driven design. So let's see. Say we have a meetup data class and we create an instance. Well, I think now just something happened, which is probably not in our interest. Do you see it? Yeah, you see it? Cool. Yeah, we messed up the title description. And that's not very surprising because, well, there are two strings and before you know it, you mess it up. Then you might say, okay, we have named arguments, so we fix that. That's true, but you have to use them. If you don't, you still can easily shoot yourself in the foot. So how could we come up with a better solution that really fixes that? Well, what we could do is use value classes. Who has heard of value classes? Not everyone, cool, so probably learned something new today. So what are value classes? Value classes are simple wrappers around common types. And the cool thing about value classes is that they only exist in your source code. In your bytecode, they're gone. So you can use them without overhead, while at the same time give your domain a lot of expression. So now we have title description, which is a very clearly defined object, nicely aligned with the DDD thinking. And I think now it's kind of very hard to still make a mistake. Because now you have this title description, which is so explicit, you're probably not going to put the title in the description object, right? Okay, now let's see. This model of this domain is going to grow, and instead of having just one meetup, we get now different kind of meetups, like an on-premise meetup and an online meetup. So how can we model that? Okay, your PO just told you that, and you're going to sit down and you start thinking, how can I model that? So let's see. So when we have on-premise meetup, we have these two attributes, an address and RSVP required. And we have an online meetup, we have a stream URL. And this is how you model it. Okay, so far so good. You're going to use this object in your business logic. And the question now is this such a good idea? Probably not, right? This is very error prone. For instance, if I forget to set the RSVP required, I would end up in an illegal state exception, which is probably not what you want. Or I could kind of set the stream URL and address and, well, still, or the RSVP required and still mess things up. How can we do better? Well, this is basically where sealed interfaces and class come in. So who of you has heard of sealed? That's quite a few. Who's using sealed also? Okay, cool. That's a familiar concept. Nice. For the ones who haven't heard of it, just a quick recap. Sealed basically allows you to have a finite amount of subclasses. That's basically what it is. So that the compiler always knows of this particular interface, I only have these implementations. So you seal basically the hierarchy. That's where the term sealed comes from. So, and this actually has two benefits. So now we have, first of all, a much more expressive domain because we say it's an on-premise meetup, it's an online meetup. And we now also have only attributes associated with it. And third, when we process this particular logic, we see that because compiler knows it's finite and not infinite, you don't need to have an else case, which makes your code much less error prone. When we extend our domain, let's say we still have a hackathon meetup which would be added, then we get exactly what we want. We get a compile error because we haven't covered the third case, which exactly said what we want, because we want to kind of be notified that, hey, you also have to take care of this particular case. Whereas in the very first case with the else part in the when, code would still compile and probably at runtime will get an error. So this conciseness and precision is actually what functional programming tries to embrace. Okay, so far so good. So I think within our valley we moved on a little bit by embracing these rich, safe and expressive domain models. But of course, we want to go further. Let's say we have this piece of code and our PO comes to us and says, I want you to store this particular list of developers not only in a CSV file, but another fancy format, TSV. So, okay, I can do that. And you sit down and you say copy and you paste and you change it to TSV. That's how you could solve it. But of course, this is not what you want, right? We are serious engineers, so code duplication is evil. So let's stay away from it. So how can we do better? Well, the cool thing is to actually get to the solution, it's quite good to do a copy-paste. And then two things. So first of all, figure out which part is actually really identical. Right? And this actually will become so-called generic control structure. Then you figure out which part actually changed. And you're going to analyze this part very concisely and figure out, okay, what actually goes in this part and what goes out. So we see that here a developer goes in and a string goes out. Right? You convert a developer to a CSV, TSV line. And this you keep in mind and convert then this into a function. And then at the designated place, you will apply this function. So now we have a nice separation of concern. We have this generic control structure that is kind of burdened with the task to fetch developers, open the file and so on. But the format you write to it is kind of delegated to the one who calls this function. And as such, we now became very flexible. So no matter which format we want to write it to, we now can do this. And this is the whole concept of a higher order function. Higher order function means that I have a method that takes function as argument. I find higher order functions being used, of course, in collections. Anton has showed us many nice usages of it. However, I do not often see this concept being used in your business logic. Yet, it is a very, very powerful concept. So, should you still be new to this concept, I have a good tip for you how you can start to learn it, which is in testing. When you look at this particular test, we see that we have quite some repetition going on with creating test data and cleaning it up. And then in between, you have a bit of test code. Also here, whenever some duplication is involved, which quite happens fast in tests, depending on your hygienic standards in tests, you can do much better. So also here we say, okay, the duplicated part we kind of put into a generic console structure. We do some extension method to with some arguments. Then the test part we kind of extract into a function. So the developers we created, we pass to this function, which then the test can use to do what it wants to use. And at the end, things are cleaned up. And this will be the result, which has really quite a few benefits. So first of all, we reuse logic. Second, we always have a guarantee that our test data is cleaned up. If everybody creates test data, don't have a kind of insurance that it's also cleaned up. And third, now our test focuses on what's really relevant for the test, which is, well, what you want to test, and not the creation and deletion of test data. Okay, so once we start to embrace these higher order functions, we definitely moved up into the higher regions, the abandoned heights of higher order functions. Yet we're still not standing on this peak. This is where we want to get to, right? We want to reach the peak. Okay, so let's recap. The higher order functions we just created before, they kind of lacked some sort of abstraction that I can combine them and create some new valuable results. So what they basically lacked is something like composability. Okay. Now the interesting thing is that the first example I showed you with the collections, there we had this capability, right? You have collections with the higher order functions which allow me to combine or transform the data in a million ways just to fit my own particular use case. So apparently this collection container with these higher order functions gave me this capability. So would it not be interesting to figure out what kind of fundamental aspects govern these characteristics? Because should we kind of decode that, should we be able to hack that, then we maybe could create our own data structures that behave in a similar composable way beyond collections. Okay? Well, and if this is our quest, then we actually enter the domain of category theory. So who of you has heard of category theory? Quite a few, yes. So category theory is the theory of mathematical structures and their relations. That sounds very vague, right? The way I compare it often is with the periodic table. You know the periodic table in physics with all the atoms? These are actually the kind of lowest level structures. And then you can create out of these molecule, out of these atoms, molecules, which have very different traits and characteristics. And the same actually applies for what you see in category theory for these logical building blocks. So instead of having atoms or physical matter pieces, now we have logical building blocks, which we can kind of arrange to get higher order building blocks. However, this category theory is also a bit of a danger zone, right? There are very weird terms hanging around there, which you probably have to face. And in that sense, it's really a mountain, because on a mountain you can climb very high, but you also can fall very deep, right? So that's where the danger comes in. So why is it a danger zone? I think what's important to realize is category theory is not developed for software development, right? Category theory, it's much broader than that. However, software development kind of is really a nice space for category theory. So, and because category theory has these fancy terms, they didn't kind of reinvent the terms for software development. Yet these terms are quite a big hurdle to kind of grasp what we try to achieve here. So many developers, they stand just below this mountain, they look up and they just see this fog, right? And they say, oh my God, get me away from here, I want to have some sunshine. And then you have a few of us that say, okay, I like fog, let's go through this fog. And they walk up the whole mountain and they stand at the top. And it's nice, they have a nice overview, but it's, first of all, it's quite cold up there. And it's also a lonely place, right? Because you're so detached from the real world. So, and I think in both cases, you kind of fail to unlock the promising capabilities. And this is what I'm trying to achieve with the rest of my talk. Let's see how I will succeed. Okay, well, this is where this monads word come in. The cool thing about monads is, I think not everyone said, I know a monad. We all use them, all of us, on a daily basis. The way I like to think about monads is about containers, right? When you have containers, you have them, they all look the same in terms of shape, but they kind of different characteristics. A container can be just a normal container, but you also have a fireproof container, you have an air-conditioned container, you have a bomb-proof container. There are containers with different characteristics, yet from the outside they're still containers. And they all can be handled by this container infrastructure. Well, the container we're going to look right now is collection. So from a container perspective, what makes a collection useful? Let's see. So what you can do with collections is kind of combine it together, right? So you have one collection and then you have another collection and then, well, instead of having kind of two collections, you still get one collection and where all the elements of both are combined. This is how this thing behaves. If you have this behavior, then you would have something like a monoid. It's even a bit more complex than that, but just stick more or less to this definition, a monoid. Maybe the word combinable would have been nice, but it's a monoid. And here you see the interface, so you can create an empty of something, like an empty collection, and then you can combine the collection. And if you would combine an empty collection with something that's filled, it still would work, right? So that's the first characteristic. The second is that you can transform elements. We have here the map function. You probably have used map, every of you, right? So you take an element, you transform it here with the toString function, so it converts the integer to a string, and then you get a collection with the converted elements. If you have this capability, it's called a functor. Yes, very good. This is the interface. So when you have a map function to map an element to another type, then it's a functor. The third is probably the most complex, yet the most powerful. Say we have this developer, and this developer has a variety of languages she knows. If we like to have all the languages of all developers, and we use map, well, we would get a list of lists. Well, we get this additional layer we actually don't want. And this is basically where flat map comes in, which does the following. So you have a collection, you take an element out, in this case a developer, you take the languages out, which again is a container of collections. But in the end, all this additional layer is kind of flattened away. This is where the term flat map comes in, right? You map and then it's flattened. So when you now have all the three capabilities combined, the monoid, which I call the combinable, with the functor, the mappable, then you basically combined in the end with flat map, then you have something like a monad. This is basically, these are basically the core ingredients of you need to kind of have in your contract to certify for a monad. So, collections were one monad. I'm sure you know quite a few more, like optional. And then I think when you want to describe monads, there is some sort of language attached to it. We could, for instance, say, or the way you could describe it is, optional models the effect of optionality. Models the effect of. That's the important part. Let's see what I mean by that. So let's first do the monad check. Can you have an empty optional? I guess you can. Can you map an optional? Yes, you can, but here comes the cool thing. Map here has a different effect than what we've seen in our collection case. Map only will be triggered here if the optional is filled. If it was empty, it wouldn't even be triggered. Same method name, same functor, but different effect. The same is true for flat map, right? So flat would only be called if an option would be filled, and if I have another optional in my flat map, I wouldn't get an option of optionals, but the additional layer would be flattened out. Another nice building block, future. Reactive building block, there are many out there, right? Complete with future, observable, uni, mono, they all gave them the same name, but all actually the same kind of monad. So what does this monad do? Well, a future models the effect of latency, right? Such a building block eventually holds either a value or exception, but not right away. Eventually, latency. Is it a monad? Let's check the interface. Can you have an empty one? Yes, you can. So let's say we have two APIs that return those monos. how does map behave here? So what is the effect of map in this context? And we see this is actually quite different than the other effects we had in optional collections. So map would be called once this get developers by name has returned a value. Then map would be triggered. And if you would like to call 2 of these monos sequentially, that's what I do here, then you would have to use flat map because I do not want to end up with a monos of a mono. That's why I have to flatten one out. Right? So, bottom line is same names, different effects, depending on the monad you have. But they allow for composability. So all the examples is here, we compose these things together. So, what does these abstractions and confusing terminology bring us? Well, the terminology, I think, is really kind of that where really things went wrong, and we cannot fix that. Just have to live with it. But what we get with monads is, well, this ability called composability. This is the power that lies within monads. And because we now have heard of the concept, of course, we want to throw it at everything, right? We learn something new, so let's rebuild everything with monads, because we can. A good kind of use case for monads is maybe error handling. I mean, here we have these try catches, and they're not so composable, right? They're kind of discrete constructs. They do not compose. So how can we fix that? How can we make this composable? 5 minutes? Okay, well, when you want to have something composable, you need a monad. The good news is there is already a monad in the standard library which is called result. Who knows of result? Oh, okay, less than half. Okay, so what is result? It's a very simple data type. Really, it's so simple. It can either have a value or an exception, but not eventually like the reactive monad. It's just a simple wrapper that is good or bad. That's basically what it is. And it has a map and a flat method. So, okay, let's rewrite this whole thing. This was on the left with the try catch, and now on the right we use this run catching. This is actually when you start such a result chain, then you make a method call, and from there on would be a result. And from there on you can kind of nicely compose over your error handling on failure, map, get or else. That's a good question he's asking, right? How do we know in the first place that I have to kind of wrap this client get def by name into something like run catching? Well, I'm an experienced developer. I know that because when you make some remote calls, you might have some I/O exceptions. Okay, that's nice, but from the signature, it's really not evident. And this is what function people don't like. When there is something which is not expected, they hate these things. So that's why they say, okay, if you have something like that, then you have to be explicit. Okay? Let's be explicit then. So instead of returning just our developer, we now return a result of developer to clearly indicate that, hey, you also can get an exception. And I give you an API to deal with it. So let's see how this turns out. Well, more or less like that. I now return a result of language, and then I kind of compose over it. So far, so good. Let's extend our example a bit. So now we have these 3 calls. So how would code look like if we would call these 3 things in sequence, right, with these results? Well, this is more or less the code you get. Get defs by name, select, flat map, flat map, flat map, flat map. And, well, maybe you kind of seen the beauty of flat map now, but maybe your colleague hasn't yet, right? And there are definitely more colleagues than you're in this room. So that's a bit of a thing, right? So is there a better way? Yes. It is actually kind of a little peek preview on our next talk of Simon about Arrow. Arrow is a beautifully crafted library. It's really a jewel of the Kotlin ecosystem that brings you functional concepts in a very accessible and easy to use way. To bring a very short introduction, it has its own kind of monadic building blocks, a lot of infrastructure to deal with them in a very efficient way. It also has some higher order building blocks, like the ones you hear, a resource, a retry, circuit breaker, saga zone. Actually, for all kind of logic levels, you have some piece of logic, inclusive this infrastructure that allows you to deal with them in a very efficient way. And you also could create your own. The nice thing actually Arrow offers us is a kind of solution for this flat map, which works as follows, which is actually a kind of port from other languages. In other truly functional languages like Scala and Haskell, they have so-called monad comprehensions. And they allow you to omit flat map. In Kotlin we don't have this, otherwise you would have heard of it. But Arrow managed it with this function literal receiver. Remember the one? Function literal receiver, receiver lambda. Also Anton talked about in last talk. This construct is used here in a similar degree to kind of make this code, instead of nested, sequential. And the only thing you have to do is call this bind method, which is in scope. That's probably a bit the confusing part, but it's very simple. Bind is so simple. Well, what does bind do? So bind does either give you the value back it has, but if it would have got an exception, it would right away return the result with that exception. So it's kind of basic flow focus, or sunny flow focused. It gives you the value if it's there. Otherwise, the first bind that would fail, you directly got the result with the exception in it back. And as such, we can write our code in a way more decent way than this flat map nesting. So indeed, bind, you have to get used to it, but once, well. And because we now have tasted this power of composability, let's just speed up gears and see what else we can do. So the signatures I showed you just now, they're kind of limited to one monad, but well, in the real world, I need much more, right? First of all, I want to be reactive. I don't want to waste resources on my server. That's why I use a React building block. Second, of course, I want explicit, right, to show that there is exception or a real value. And while I've had it, why not use something like option that kind of tells me whether there is a value or not? All different monads. Sounds good. So let's see how this works out. By calling the service just in sequence. Well, this is what you get. Doesn't really look like calling 3 services in sequence, right? Looks a bit more complex. And you see, now it becomes very nasty. So should you encounter this particular case, where you flat map till you drop, and you might feel yourself like a bit, oh yeah, there's no business logic yet, right? So this you still have to add, it doesn't fit on the slide. Then you might feel like being in this container terminal, here on top of this crane, shifting around containers instead of writing business logic. And well, I can tell you I've been there, and I'm not going to go back. It's not that much fun, because in the end you want to write logic and not shifting around containers. So then you might think, oh, wait a minute, now we have these monad comprehensions, can they not help? The bad news is, no, they can't help, because they only work for one monad, right? But there is more kind of machinery in this functional universe, like monad transformers. So what are monad transformers? Well, they actually allow you to have a conversion of 2 monads, where you kind of convert the inner type right away. So with map T, you basically can omit mono, map, it, map. The problem is this only works for 2 levels of monads. We have 3, and well, I promise you, you're not gonna get there, because at the time you finished your flat map T inner, and you get some coffee and go back, you don't know anymore what you did, let alone your colleague. I really had this. Did I write this code? So, well, it's no fun, really no fun. Then the question would be, yeah, okay, are then these monads no good at all? Well, I said, if you can stick to one, I think you're fine. But you might say then, I need these 3. The question is, of course, do you really need them? Maybe you don't. So who of you uses monos? Or some reactive building block? Okay, few. Okay, I have good news for you. And actually, we already had it this morning in our coroutine talk. So monos disappear if you use suspend functions. It makes life so much simpler. I really would advise you to grant yourself this revelation. It's awesome. So much complexity just melts away by converting these method calls into suspend methods. perfectly works Spring Boot. We just seen it this morning, so strong advice to do that. Okay, one mono less, 2 to go. Well, this one is quite simple, right? We have a question mark, so. And as such, I think now we're back to decent kind of code. That is probably not that bad. Okay, so I think now we kind of explored this lonely peak of monadic mist, and I could kind of shut down now, but I think it still wouldn't feel that satisfactory, right? So what can we not kind of get to a better synthesis of this story? Let's see. In order to get to a better end of this story, we have to ask the question, what amount of monads is okay? Which actually brings to a much larger question, which is, what is good code? And well, many books have been written about it, and many books will be written about it. I take a quite simple stance on that. I think good code reflects the domain you're in as accurate as possible. So when you're a pet store, well, then it's about dogs, cats, dog food, and so on. And when you're a bank, probably about mortgages, shares, and so on. So in other words, your code should contain a minimum of non-domain abstractions. And if you use non-domain abstractions, they should serve a very clear purpose. As such that when you have a domain expert that's not a technical person, read through your code, still kind of can grasp what's going on, instead of just being flattened by all these flat maps, right? That's not really domain knowledge you can associate to. In other words, if your code looks like this, well, then you probably missed the point. Unless your company is a terminal kernel, right? Then it's fine. That's the only exception. So now, to finish up, I'd like to kind of show you the effect of what you get when you start throwing monads blindly at your code. This is what you see here. We have a layered application, some data access layer, we have some service layer, then we have some API layer, controller, and in the end, probably also some exception handler. And what we use here is actually a result type to be explicit and so on, all the benefits I described in the beginnings. But when you look closely, then you see that we basically kind of pass things on and on and on, and in the end we convert to an exception and return our result. So what's the big deal? Why are we doing all this? Doesn't really add a lot of value, right? So we can say that in 95% of all cases, we don't use them anyway, so why declare them? This code looks cleaner, right? But of course, there is this 5%. So let's see. In our basic flow, we've seen that probably we do not need monads. In the case where something goes wrong, really terribly wrong, no connection to database, well, what do you want to do with monads? We have an exception. You just want to send something 500 in a decent JSON back. However, in cases where you might recover from a certain API call, and depending on that, still return OK response or return an exception, it might be valuable to have an explicit interface of what kind of errors you can expect. So there might be interesting. By the way, I would never opt for result. Why not? Well, I'm going to show you. So this is the result type. Map would be for the good value. Recover catching would be recovering from a bad value. And the problem is because a result holds an exception, dealing with or using exceptions in your business logic to define what else needs to happen is of course not what you want, right? Using exceptions for control flow is an anti-pattern. There's a reason for that. So when you build all your monadic logic on result, this is what you end up with. Alternative cases would have to use exceptions to figure out what to do next. That's probably not what you want. That's why I would strongly advise to use either. Either set is a very simple data type, which is very close to result, but it's more versatile. So this here, it's a superclass has two that can be of two things, a left or a right. That's it. It can be a left or a right. Normally left is the bad part and right is always right? So that's why right is good. So then you also have kind of operators to deal with it. And now our signature becomes much more expressive in a sense that I say, again, an either of an API error or language. An API error is, again, such a sealed hierarchy where we can use the benefits we discussed in the beginning of our presentation, where you clearly show that this is my hierarchy you can deal with in an exhaustive manner. And then by, well, using one of those operators like handle, error, with, or whatever operator you want, now get a clear list of what to deal with in this particular case. And as such, if I then would have to apply them, for instance, for database stuff, probably wouldn't use even a monad because, well, if database something goes wrong, right? You cannot recover. So no need to have an either there. In our API, maybe it makes sense because we can recover from it. And when you have to recover, you now have this decent code you can write to deal with it in a, well, in okay-ish way. Once we've done with it, we still could opt to just simply throw this exception, that our default mechanism of exception handling still be in place. So this is basically the gist of pick the best, skip the rest, use it locally, selectively, where it makes sense, but not just throw it blindly at it. And as such, you definitely will benefit a lot. At least that's my experience. And I've gone both ways, so it's justified to a certain degree. Yeah, I think time is up, more or less, I guess, right? So, well, if we had some examples, so if we are able to embrace functional programming in that way, so that for the problem at hand, we choose the right building blocks, instead of just kind of blindly follow the newest golden hammer rule, then we enter this prosperous LP made out of functional common sense, where it's quite pleasant, right? Because when you need it, it's still there, this mountain, but you're not standing at a place nobody can reach, still a place you can reach. It's a nice overview. It's a very convenient way to live. And that's also really my experience I've had so far. Thank you.